two computers is a bit of coordination, but hey, we got it going. Properties of color. So we already talked probably briefly about this before. I think we did, in fact, that light is on the spectrum of electromagnetic energy. So light is the only visible energy. All the other energy that's out there is not visible. Our eyes have evolved, adapted, whatever you wish to describe it as, to that fact. So light is found between ultraviolet and infrared. So as the wavelengths get shorter, they go towards ultraviolet, and as they're longer, they head towards infrared. Okay, so and I say that because a lot of the charts and graphs are how do I explain this? So this chart isn't labeled particularly, but it is showing you going from long wavelengths on the right-hand side of the chart to short wavelengths on the left-hand side of the chart. A lot of these spectrum charts are flipped both ways because whether they're talking frequency or wavelength, it's what depends on the orientation of the chart. But regardless of that, what's important to understand, not so much the wavelength per se, because we're not at that level, but what's important to understand is the relationship. So one of the relationships is that the lowest wavelength of light, the longest wavelengths, I'm sorry, of light, are adjacent to infrared, which is heat. Okay. Someone's got their mic. If someone's cooking in there, or I don't know who that is. Who is that? Nasheed, you're the one making the noise.
I'm sorry.
You're not cooking, are you? That's all right.
Sorry.
That's all right. It'll be on the recording forever. Just remember that this is being recorded, so this is now going to be immortalized. Where was I? So yeah, so remembering that infrared is heat, and that red light is adjacent to heat. So in other words, if you increase the wavelength of heat, it ends up becoming red light. This will become important when we talk later on about color temperature. And then at the other end of the scale, blue light, if you increase the wavelength beyond normal blue light, you get into ultraviolet. Okay, so that's really what's important about where the light belongs on the spectrum. Is that on one side of that color spectrum, the reds, just below that in wavelength length is is heat, and on the other side on blue, above that in shorter wavelengths is ultraviolet and beyond. Okay. All right, so moving on. Right, so of course, here's the chart again, same orientation. Light is waves except when it's not. So the reason I say that, of course, is because we've talked before about how light can be particles, and how it behaves as both depending on what we're talking about. For example, the camera sensors, as we learned last week, it's the particle action of light that we look at. It's the fact that a photon displaces an electron, and that creates energy on the camera sensor. Now we're talking again, we're going back to talking about light as a wave, because we're going to talk about frequencies, wavelengths, amplitude, all the characteristics that waves have, okay? And again, this chart shows you kind of where light fits into the world of infrared and ultraviolet and all that stuff. All right. Oh, this is weird. I keep trying to change slides on the wrong computer. Oh yeah, so the qualities of color, because we're talking about waves, it's the same basically as the quality of sound, in that we have wavelength, intensity, brightness, hue, chroma, and luminance. Wavelength, when we talk about sound, in the case of light, wavelength and frequency, we can kind of use them interchangeably. With sound, it's a little different. But with light, because we see the phenomena of wavelength / frequency in the same way. In other words, a shorter wavelength presents as one color, a higher frequency presents as one color. So they're essentially interchangeable. Chroma is the intensity. It's how much color, sorry, not how much light. Chroma is how much color there is, and luminance is how much brightness, how much light there is. And those last two often get confused. They're not the same thing. If you want to use a metaphor, and it's difficult because people start thinking about paint as light, and it's not. But if you imagine that we're talking about paint for a second, chroma would be the amount of pigment in the paint, and luminance would be how much white you would add to that paint to make it brighter. Does that make any sense? So in light, you don't do those things because there's no pigment. But in light, we increase the intensity, which is the energy around that frequency to get that color. With luminance, we increase basically all the energy in the light beam to make everything brighter. Okay, so that's the difference between chroma and luminance, and we'll discuss that a bit more as we progress. Hue is what we, and I say we, I use the term the royal we as industry folk. Hue is what we would call color. So civilians, and I learned that term from a friend of mine many years ago, people who are not in the industry, civilians, refer to color sort of haphazardly, anything's a color. But to us, we don't use terms like color to describe the actual things, so we want to break them down more specifically, and so we use hue to describe what most people would call color. So when you talk about those 5 dots on the screen, you've got cyan, magenta, which so the top one is a mixture of 100% both. The second one is 100% magenta. The third one is 100% magenta and yellow and on. These are just mixed up versions. Each one of those 5 presents a color to the average person, but what we would say is that the hue, and the hue would be measured in those percentages or in numbers, such as in Photoshop, where you have the 255 scale or 1024. Yes. So where was I going with this? Oh yeah, so hue is what we would call color. It is the frequency aspect of light, which is also the wavelength, right? Because as we said before, wavelength and frequency are proportional. The longer the wavelength, the shorter the longer the frequency. The lower the frequency, I'm sorry, the shorter the wavelength, the higher the frequency. And that's just physics. The closer together the waves are, in the sense that the wavelength is shorter, the more quickly they occur, which means the frequency is higher, right? So that's how they're related, in case anyone is confused. All righty, so that's hue. And as I said, hue is frequency. So the important thing to remember is that every spectral hue, now when we talk about spectral hues, this is an important thing to remember. We're talking about rainbow colors, and these are the natural colors provided by sunlight. All right. Artificial light has its own characteristics. We'll talk a little bit about that later, but sunlight has specific colors in it. And one of the things about sunlight is that there's no magenta in sunlight. That's a color we quote unquote invented in order to make our color measurement work. And in fact, I could probably show, you know what, let's just stop the share here. I could probably show this video. No, don't show that video. I could probably show, wait. Hang on. I didn't have it queued up. It was going so well. There we go. Okay, so we take this, we stop, we share again. All right, here's a quick explanation about why sunlight is unique.
Told that the colors of the rainbow correspond to...
Missed the first word.
We've all been told that the colors of the rainbow correspond to different wavelengths of visible light. Red, orange, yellow, green, blue, and violet. Where's pink in that list? It's not there. There's simply no pink light. So where does pink come from? It turns out that pink, or magenta, fuchsia, or whatever you want to call it, is actually a mix of red and blue light. Light from both ends of the rainbow that our brains see as one single color. If you try to roll up the rainbow to make a color wheel, there'll be a gap between red and violet. That's where all of the rest of the light in the universe is supposed to go. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, and so on. But since we can't see any of those wavelengths, we replace all that hidden grandeur with pink. And speaking in terms of light, pink should probably be called minus green, because pink is just the leftovers of white light when you take out the green.
Okay, so basically that states it right there, right? There is no natural light that's magenta or pink, and the reason we have it at all is because we created a color wheel, we created measurement tools, and in order to have those color wheels meet, like for example, as he showed, the 2 ends of the color wheel have to meet. In order for that to happen, you got to put something there, and what you do is they put a mixture of the colors from either end, the ultraviolet and the infrared, and put them together. What do you get? Red and blue, pink, right? So anyway, in light anyway. It's different with pigment. I know people are saying you get mixed red and blue paint, you get purple. It's a whole other story. That's pigment, not light. Okay, so let's go back to this and continue. Okay, so no pink light. Each light has its own wavelength and frequency. And as you can see here in this diagram, the spaghetti shapes of the various colors, right? Okay. So chroma, what is chroma? Chroma is also known as intensity. It's sometimes called saturation. It's intensity in the sense of the color. So it's not, it's when you talk about chroma and you talk about intensity, you always put it in the context of color, because intensity can be misleading, which is why we often use the term saturation. Again, industry folks will know that saturation is specifically talking about chroma, color saturation, right? And you'll probably see saturation more often, but intensity is a term you can use, but you would normally say it as something like chroma intensity or color intensity, right? And what chroma, again, is how much color is going on. So if you look at this pie chart, what we have got in this pie chart is that as we go around the chart, the percentage of colors mixed together, the cyan yellow percentages match all the way around that pie chart, but we keep increasing the amount and we end up with more intensity, more saturation, all right? So what you're seeing in this wheel is the same color, and it's the same color because the formula to make it, remember that colors in the RGB color system, and I'm not sure, maybe I didn't say this clearly before, the colors in the RGB color system are made up of the three components, red, green, and blue, right? This is showing black because this is actually a CMYK diagram. Don't let that black fool you. But nonetheless, the principle is true, and this illustration is actually pretty good. The colors RGB make up all the other colors in their various combinations by just mixing the various proportions. So if you keep the proportions the same, you have the same hue, right? But it gets darker, it gets more intense if you keep adding quantity. So 15% cyan, and then double that, you get this, you know, increase it by 25%, 50% again, and on around this wheel. The hue remains constant, but the intensity increases. Now, if you're looking at your screen at home and you're wondering, well, why do these colors look slightly different? That's the fault of the computer and the graphic. They shouldn't look different. They do. There's almost no way to fix it without spending hours and hours of trying to do all kinds of color matching. And for the sake of this diagram, the point is that even if it looks a bit different, all it's really changing is the intensity. All right. In reality, if you were doing this professionally, these would look the same. You can see that the one at 9 o'clock is a little bit off compared to the others. That's just a flaw of the graphic itself. Okay, so increasing the chroma increases the amount of saturation, the amount of color in the element. So chroma specifically refers to the comparison of a color to a neutral gray. All right, so whenever you're talking about chroma, you're referring it to neutral gray. And the trick with neutral gray is, and I'm not sure if I write this in the slides. No, I don't. So I'm going to say it out loud, but make a note of this because there's a quiz question about this point. And that is neutral gray is any color where all three primaries, red, green, and blue, are mixed at equal level. So if in this example, and I probably should have illustrated this, if we had a diagram where I had red, green, and blue instead of cyan, yellow, and black, and I made red, green, and blue equal, so 10%, 10%, 10%, the result would be gray. I guarantee you that. If you have RGB and you have R1, B1, G1, it's gray. RGB, if you have R50, B50, G50, it's gray. Now here's the difference. R0, B0, G0 are black because there's no color, right? So that's one exception. And the other exception is if we're using this numbering system I'm using from 8-bit color, where 255 is maximum. If you go to maximum, R255, G255, B255, it's white. But every other color in between, RGB0 and RGB255, is gray if the R, G, and B values are equal. And you can test that yourselves. Go into Photoshop, open up a new document, drop a shape in the middle of the document and change the colors and just keep changing the R, G, and B values to the same number. And as you do it, you'll notice that it keeps changing to gray. So that's the neutral gray I'm talking about. So when we talk about chroma, we're referring it to that neutral gray. Okay, that's just so you know the basis of this. It'll be important when you get into color correction because you have to have a reference point. So for a color corrector, You'll notice, for example, that a lot of cameras, camera operators and stuff put up charts, and I should, I'll stop. You know what? I'm going to stop for a sec. I'm starting to talk without imagery, and that bugs me a little bit. Let me just get a camera chart up and we'll show it to you. I'll just stall it here. Yeah. The problem with having two computers is you haven't got two people, so you still have to stop one thing and do another. I want a camera color chart. Hang on a second. Here we go. Here we go. ISO chart. View. No. Don't do that. Don't buy it. Yeah, there we go. Not want to buy. I just want to look at it. Okay, let's share. Let's have a look at this just for a second. This is a bit of a sidebar, but let's have a look. Okay, so here's a camera chart. Some of you might have seen this before. This is becoming more common than the older charts. And it has a lot of different colors on it, which have a lot of different meanings. But the bottom, excuse me, the bottom row is gray, right? And these are all 5, 6, chips where the R, G, and B values are equal. Okay. Now, if you're a colorist, this is one of your reference points, because it's easy to check. These a little bit more problematic, unless you know these values, and a professional will know these values. But for the amateur, the person first starting out, gray is your friend. Every camera operator should carry a gray card with them, as well as a white balance card, because the colorist will appreciate it later on. Because in order for gray to be gray, all 3 values must equal. So why is that important? Well, if you shoot this chart with a camera, and then you're in editing looking at this chart on the beginning of your footage, and you don't need to do this for every setup. You should only change the chart when you change the lighting, but anyway, or reposition to a new location. If you shoot this chart, in editing, you look at it and you notice that this middle gray here is, let's say, R100, G105, B100. That means it's got a bit of extra green in it. The whole image now has, you realize, because this is your reference point, it's supposed to be R100, B100, G100, but it's R100, B100, G105. You now realize you've got to remove 5% green from the entire image to balance this gray to neutral, right? That's why this is important to understand that. It's not important when you're shooting it. The camera people don't really care. And in fact, camera operators didn't used to carry these particular charts because it didn't matter to them. They were more concerned about the camera's operation. But now that we're moving on to coloring and color correction becoming much more accessible, this is the kind of card you should have, and you can buy these anywhere. Do not print one out. Like, do not, unless it's an actual physical chart you've bought, don't trust it. Don't shoot it off of a screen, because you don't have any idea what those materials, the printer, the screen, are doing to this chart. You need the actual physical chart. It is your rock when it comes to color correction and color reference, all right? Because if your printer is not quite right, if your screen that you're shooting to get this as a reference isn't quite right, and I mean, you could theoretically shoot this off of a screen to use it as a reference, but you would have had to have calibrated your screen beforehand, and that's an expensive proposition. Anyway, again, I digress. Let's go back to sharing and talk about the chroma. But that is why chroma is referenced to that neutral gray. Once you've got that neutral gray reference, you can now know where all your colors are supposed to be. All right. And so again, this chart, as imperfect as it is, and I should probably custom make my own. As you can see by the credit at the bottom there, I kind of lifted this from someone else. But as you can see, by changing the values, you change the intensity, but the color remains the same. And the luminance remains the same, by the way, too, right? The brightness is the same. It's just the intensity is changing. How much color is there is the bottom line. Chroma is how much color is there. Okay, one way to see hue and chroma, we talked about hue and chroma, is the vector scope. We'll talk about scopes a bit later on this term, but this is our introduction to that concept. And the vector scope here is based on Maxwell's triangle, which we'll talk about also briefly. And Maxwell and Newton, the two of them together, came up with the idea of orienting the colors into a wheel or a circle. I shouldn't say they invented it, but they perfected it. And that allows us humans to place them in our minds, right? So the only reason we have these circular and triangular and various other shapy color diagrams is because we humans can't understand the abstract idea of a color spectrum. So we have to diagram it. The CIE diagram is very easy to understand once you figure it out. It tells you what you can see in the way of colors, right? So just remember that that's, again, if you're in the editing program and you get lost and you wonder, what the heck am I looking at here? So if you want to know, for example, a quick thing you learn as a professional is that red, most people have blood in their veins, right? That's a given. I hope that's not a controversial comment. But most people have blood in their veins, which means that flesh tones, regardless of skin color, although skin color will affect flesh tones will mostly be heading towards red, right? So you can see this person does not have a light complexion. She's a dark complexion, and yet, and I know that there's some red in the image. There's some flags and things, so that's some of this really excessive red that's way up here. Skin color wouldn't normally be that much different than the other colors. So skin color is buried down in here, but this little sort of knob that's coming off at around 12 o'clock-ish is going to indicate that person's face and flesh tone. And so I say that because, again, once it's like driving a car. Once you recognize all these various little bits and pieces, you don't have to keep looking them up. You'll know after a while. You'll look at this diagram and go, oh, there's the face right there. Now, why is that important? Because if these flesh tones are actually over this way a little bit or going this way a little bit, then the white balance is incorrect. The color balance is incorrect. Nobody should, unless they're wearing makeup, or unless it's an effect, nobody's flesh should have tones other than red. I shouldn't say other than red. Should have flesh tones that aren't red. Let's put it that way. Okay. So the vector scope is one way and one tool, and you've all got access to that in Avid, in Premiere. If you open up the scopes panel, the lumetri panels in Premiere, I think it's called scopes in Avid. I forget what, I think it's in the color correction tool in Resolve. You'll see all this stuff. I think this is in fact from Resolve, if I'm not mistaken. This is the diagram. Okay. Moving on. What is luminance? So luminance is the amount of energy in a color. Okay, so this is where we get into confusion with the chroma. So this is not the amount of intensity in a specific color or group of colors. It's the energy. It's the overall number of photons. Let's put it that way. Let's relate it back to photons for a second. Whereas chroma, although related to photons indirectly, is more about the frequency because it's the color. Right? Just keep that in mind. Chroma is a color property, so it's really concerned with the frequency. Luminance is really concerned with the intensity of the image, the amount of energy that is being used to create that image. How much light, how many electrons coming off the sensor, that is luminance. Okay? How bright is it, is a way to put it. Regardless of the color, that's the other thing to keep in mind. Luminance does not depend on the color, although because it's RGB, you can combine colors and increase luminance, absolutely. But luminance itself is a separate property from color. And why do I say that? Because you can have a black and white monochrome image, which has luminance. It doesn't have any color, right? But it still has luminance. It has no chroma. It has no hue, but it would have luminance. So luminance is a standalone property of the brightness. Sometimes called brightness, sometimes called contrast. Both of those are imperfect terms. Even there's an argument, I'll tell you right now, in the industry about luminance versus luma. We'll talk about that in a minute. Luma is what video people call luminance. Lighting people insist that luminance and luma are two different things, and so the fight begins, right? We're in this world nowadays where almost any fact you present is arguable, which is unfortunate, but and I know this because I've done research on this topic, and I could have spent a half an hour trying to explain the hair splitting between luminance and luma. There's in fact quite a scholarly article written by a fellow named Charles Poynton, and he's a television scholar, and he went on for pages about the difference between luma and luminance. But you know what? 90%, except those people who love to argue, maybe, and those people who want to be precisely scientifically correct, maybe, 90% of the people you come across will use luminance and luma interchangeably. Okay. The exception to that is lighting people. Lighting people will take exception because lighting people don't talk about luma at all because they're dealing with physical lights. They're not dealing with electronic video levels, right? Luma is really a property of video levels, just so you understand. Luminance is a property of both. Anyway, sorry, I don't mean to digress, but that is because you'll do some Googling on this and find the contrast. Now, just to make it even more confusing, the symbol for luma is Y. All right, and here comes the dad joke. Why is that? Because it's the up and down axis of the chart. Because it's the energy plot. So if you imagine a graph where X goes across the bottom, X would be, say, the frequency, let's say, for example. Typically, in almost every graph, the up and down part of the graph is Y. It's the energy, right? Amplitude for sound, brightness for light. those kind of things. As a result of that, luma, the symbol for luma is Y off that Y axis on any graph. Okay. If you're not a mathy person, don't worry about it. It's still Y. Now, some people, again, when I say some people at the bottom use Y apostrophe, those are the people who argue that luma and luminance are two different things. So to them, luma is Y apostrophe and luminance is Y. I've just put it out there as a fact, but don't worry about it. Just use Y. Okay, so I'm not sure why I showed this same chart. Oh, right, because we'll go back to our chart with the chroma. So here we have, again, we've been increasing the color intensity, and each one of these wedges of the pie should, theoretically speaking, be the same brightness, right? What tends to happen, and this is why I keep going back to this chart, is that we look at that one that's at the top right, the cyan 15, yellow 15, black 0, and we think instinctively that is brighter than the one right next to it with 100% at 0, right? That's just perception, and that's also training. We've been trained to think that whiter is brighter, let's put it that way. It doesn't necessarily have to be, and professionally you'll discover as you start measuring things that it isn't. Okay, so you've got to break yourself of the habit of thinking because it's a whiter, closer to white. So, and the reason that 15-15-0 is closer to white, of course, is because 0-0-0 would be white, right? So we've only got 15% color in this one wedge. But we tend to think, and this is, again, something you have to break your mind out of, is your conventional upbringing, sort of non-industry, non-color theory upbringing, is to imagine that whiter is brighter. But in fact, the lumina value, the brightness value of these two charts, these two pies, the 100-100-0 and the 15-15-0 are the same. Okay, that's all I want to get across there. But it doesn't look the same. It'll measure the same on a vector scope, on a waveform monitor when you're doing your scopes, but it isn't. It is the same. It looks different, but that's just illusion. I shouldn't say it's illusion. Let me go back. It is true that it looks brighter because that's how you've been taught to think of it. I guess that's what I'm trying to say. You've been taught to think that 15-15-0 is brighter than 100-100-0. Right? It is more vibrant in some respects, but it's the same brightness value. I guess that's what I'm going to say. Enough about that. Okay, so here's an example now of changing the brightness, and I had to simulate this because on a slide, even on a computer, this is hard to do without an actual moving picture, and say if we're sitting down in front of Resolve or something with some color tools. So I've simulated this idea of you look at the same hue, so you have the same color mixtures on those three stripes on left and the right, but on the right we have more brightness. Okay, now it looks fainter because I'm simulating it, but in fact, if this was light, if I added more energy to the one on the right, it would be brighter, but the hues would be the same. The red is the same, the green is the same, the blue is the same, okay? So for the sake of professionals, these three stripes are the same colors, okay? The same hue, the same color. So I pause there because, again, our training is that if there's a quality difference in the two stripes, for example, the two red stripes have different intensities or whatever, we would automatically think they're different colors. And if you're doing paint, if you're doing CMYK work, you would be correct. These would be different colors. And in fact, in the world of CMYK, anyone who's gone to a hardware store knows this, every paint chip has a name. So the one on the left might be, crimson, and the one on the right might be dusky rose, right? And that tends to be a habit. Pantone is a good example, where Pantone, instead of a name, they assign a number, right, to every single color, because that is kind of how the CMYK system has evolved, is that every color has to have a name. In the RGB color system, we don't necessarily name all these colors. And in fact, we would say that these three stripes are the same color on both sides. But we don't use the word color because that's imprecise. We use the word hue. Okay? Cool. Remembering that as we talk about vision, human vision has what's called a finer spatial sensitivity to luminance. And what that fancy first paragraph means is we can see black and white brightness changes better than we can see color changes. Okay? And we use that very weapon against ourselves when we talk about color and digitizing, for example, and in fact, not even in analog, we use the same tool. We always, since the beginning of television, and even I would even argue, without any academic backing up here, that even in the days of film, the color information was not as precise as the black and white information on an image. Black and white photographs always look sharper because that's how we're conditioned from evolution and training to look at everything. Color information doesn't need to be as precise to fool us. I use the word fool us because, in fact, we can and will and do right now. In fact, you're looking at one. We take an image where the actual true color information has been removed to some degree, but not enough to affect our perception of it. Okay, again, I'll pause because that might be a bit of a mind blow. So remembering that almost everything we look at with video is an illusion. This red that we're seeing on this diagram here isn't as red as it would be in real life. And we don't care about that. We don't notice that. But if this red was darker, if this stripe had less brightness than the green stripe, we would notice that right away. And that's just how we are. Our eyes have evolved, our brains have evolved to be much more aware. And that goes back to the fact that if you look at our animal origins, our caveman origins, our primitive origins, the fastest way to survive was to see something moving in the dark. You didn't care what color it was. You started running before you even knew what it was, but you saw something move. And the only thing you could see move were shadows. Shadows have no color information. So that's what saved you, right? We evolved having a much higher perception of monochrome because it was survival, okay? And then we only evolved enough color to keep thriving. We didn't need to evolve a more distinct color sense than we already have. Other animals have a much higher color sense than us because they have different needs for it, all right? So anyway, a long way to hang on this slide and say that this whole idea of color sampling being less precise is the whole basis for digital video and photography. And we'll get into that when we talk about codecs and digital and analog. Color subsampling is the very first thing, and subsampling means sampling less often than necessary as one of the very first tricks you do to try and reduce data in a digital signal, okay? So it's because luma over chroma for us humans. That's the whole point there. Brightness changes are much more noticeable and important. All right. Another tool to see luma, a tool to see luma, we talked about the tool to see hue before, which was the vector scope, is the waveform monitor. And this is, I think, a screenshot of Premiere from the Lumetri panels, if I'm not mistaken. In any case, this on the right is the waveform monitor. And all the waveform monitor is showing us is black at the 0 point. And apologies for this diagram being so indistinct. So this is the picture we're measuring, and this is the measurement we're getting, okay? And all we're seeing here is black at the bottom, which is where almost all this bottom is resting, because there's a lot of black. So again, you'll learn to read these things as you progress in your career. But you can see right away there's a lot of shadow in the picture because there's a thick black area thick green, area at the bottom of this scope, and that corresponds to these shadows up here, right? If these shadows weren't there, this would not be here. And if you look at the very tops, you see the little tiny dots of the brightness. Now, white is way at the top. So the first thing you know as a professional, there's no white in this picture, but there are bright things, and they're very distinct and small. So you look at the picture, what do you see that's distinct and small? You see leaves, right? You see some reflections on these leaves, right? On and on. And then in the middle here is all the other brightness. And all this chart, all this scope is showing you is how bright it is from 0 to 100, right? And that's called the waveform monitor, because this shape back in the early days was a wave form and has been molded into this eventual diagram. All right. Okay, so a quick, you know what, let's just pause. Let's just pause for a second. And we'll do a pause on the record. So remembering, of course, additive as subtractive, and here's the two primaries, RGB, CMY, and of course the K in CMYK is the extra black that's added because of the imperfect nature of ink. So for every color, and now we're talking, of course, about the RGB system, but it's true in CMYK. but we're talking RGB, specifically because of the way these colors relate. They relate differently in CMYK a little bit. But anyway, for every color, there is a complementary color, all right? And so this is, again, the nature of that vector scope color wheel that we had back here, right? So when we're doing, and why this is important, this complementary thing, is because when we're doing color correction, if you want to remove red, you add the complementary color on the other side, and that pulls the red across, it pulls the colors towards. So by adding energy to this, all these colors start to move this way, right? It's like a bit of a magnet if you think of it. So if we go back to the color wheel here, if red is the color we want to remove, we add a bit of cyan. If cyan is the color you want to remove, you add a bit of red. If you want to remove blue, you add a bit of yellow, right? Now you guys know probably the blue and yellow one when we talk about color filters for lights, right? You've got to put orange filters on the lights. The orange is probably closer to the yellow-red border. I mean, remember, these boundaries between the colors aren't firm. You know, they gradually shift from yellow to red to magenta, but this pie chart is for diagrams only. But the orange gel that you put on the light is somewhere in here. It adds orange to the light, which does what? It reduces the blue, right? That's why you're adding those orange gels to lights. By adding the orange to the light, you reduce the blue, okay? And that's because you're dealing with light. It's additive. The only way to make color changes is to add. You can't really subtract so much as you can add the complement, okay? And understand too that when you subtract, if you use programs like Photoshop that let you subtract mathematically, by subtracting the blue, because the balance of the three colors has to remain constant, by subtracting the blue, you are in effect adding the orange anyway, right? Reducing the blue makes the image turn a bit orange. And try it. Take a picture, go into Photoshop, subtract a bit of blue, go to the RGB and alter the colors, change a bit of blue. You'll notice the image turns a bit orange. It adds a bit of orange. So that's how this right here is the basis of color correction, is understand your complementary colors. Now there's not just six colors, there's the whole range of hues, right? But that's why we have this, tool, so that we can see as we make changes on one side of the color wheel, we can watch the changes happen. You can't just eyeball everything. All right. So what's the key with complementary colors? When you combine the two colors together, the complementary and the primary across from it, you get white, okay? So if you combine, well, here, this has actually got better. If you combine the R and B, which is the complementary of green, which is here, magenta, right? Again, these colors, apologies, these colors aren't perfect because again, these charts and renderings on computers aren't the greatest, but this magenta here is a combination of red and blue, right? Magenta is, all these colors are combinations of their neighbors, right? So if you take the magenta as a combination of red and blue, you add that to green to get white. You take the cyan, which is a combination of green and blue, to red, you get white. You take the yellow, which is a combination of red and green, you get blue. I mean, sorry, you get white. Okay. So another important thing to remember, this sometimes is a revelation to some people, that you get yellow in light by adding red and green together, right? But how many of us were raised with the idea that you make green by adding blue and yellow together? Well, why is that? Because when you're making green pigment, you're using a different color system, and the formulas are different to make the colors because it's reflective, it's not additive, right? That's why the formula for yellow in paint, ink, coloring pencils, crayons, sidewalk chalk is blue plus yellow equals green, right? But you get yellow by mixing red and green in additive color. So just keep that in mind. Anyway, moving on. So that's enough about that. Complementary colors, hopefully that's pretty clear. Now we're going to talk a bit about the diagram again. So the fellow named Maxwell, James Clerk Maxwell, don't remember all of that, just Maxwell's triangle. Maxwell's triangle is important because it was one of the first diagrams to represent colors and how they relate to each other. It's one of the diagrams that's responsible for the creation of magenta as a colored light, right? Which is an artificial, as we learned already, there's no pink light, right? But in order to make the diagram work, we had to join the two sides together. In nature, let's go back just quickly all the way back up the top here. In nature, the spectrum never meets, right? The two ends of the color spectrum never meet. They start here and they progress in changes in a wavelength to the other end. The blue and the red are never together in nature, never. It's not how it works. But for us humans, we need to take all these colors and start organizing them in some kind of way, you know, like a catalog or some sort of file system. So we come up with all these shapes to help us, right? And one of the shapes is the triangle. The triangle evolved into the circle eventually. It became this, but it started with this. And that created this idea that you had to meet. And when the red and the blue met, which don't meet in nature, what's in the middle? Can't be nothing. So it's a mixture of red and blue, which is magenta. So understand when I say this, that I'm not saying magenta light doesn't exist. What I'm saying is it doesn't exist in nature. It's an artificial creation by mixing red and blue, which would never happen in reality. I shouldn't say reality, in nature. Light from the sun would never create magenta light. We can create magenta light artificially, easy peasy, by just mixing the red and blue frequencies together, okay? All right, so Maxwell triangle, diagram, color relationships. The corners represent the three primaries. This is a much more slimmed down version. This is one of Maxwell's actual diagrams, by the way, or a diagram produced through his teaching. This is a more simplified version for us to understand. The corners represent the three primaries. The sides are fully saturated, which means that if you can't go any further out than the side of the triangle, you cannot go beyond this level of saturation. There's no more color information available. So the sides limit the saturation, and the center is white. The middle of where if you draw a straight line from the corner to the middle, that's the complementary color, right? If you bring it in and reduce the saturation of that color a little bit, that's lowering the chroma. It's the same color. It's on that same line, right? I don't know if that cursor is sort of disappearing and reappearing. Make sense? I hope. White is in the geometric middle of the triangle. It is not in the geometric middle of the CIE diagram. That's a bit of a different diagram because that also shows our sensitivity. But when we're diagramming color, we don't care about human sensitivity. We just care about relationships to the colors. So in the case of both the vector scope and Maxwell's triangle, white is in the center. I'll show you a diagram of white later on when we talk about white balancing. Okay, so hue is the direction from the point of the center. So there is no hue in the middle of the triangle, in the middle of the vector scope diagram. There's no hue, it's just white. Okay, so it's equal colors in all directions, and then as you move out, the hue increases, and as does the saturation. So the hue increases as you go around, or I shouldn't say increases. The hue changes as you go around. It nulls out in the center. Okay, there's no black on this triangle because you can't make black by mixing colors together, right? It's only an absence of color for black in the RGB system. So the only way the diagram is going to show you a mixture result is the white in the center. So hue, the moment you move off the center of this diagram, you have hue added. And then as you get further out to the edges, you add the chroma, the saturation as well, right? So as you go around the circle, the hue changes. If you stay in the same place as you go around, the chroma saturation is the same. If you move outwards, the saturation increases, okay? So that's Maxwell's triangle. You will probably not deal with Maxwell's triangle. You'll be dealing with this shape on the right, the vector scope, but it's the basis for that triangle. I prefer the vector scope because it's a lot easier to understand for me, but then I've been using this vector scope for a long time, so it's kind of second nature to me. You're seeing, so for example, if you look at this diagram here, you're seeing color bar, and color bar is a test signal. You may not have seen color bar before, but what this is doing is calibrating the vector scope to make sure that all the colors are in their proper places. Right. So these boxes on the vector scope, and we'll talk about this when we talk about the scope lesson later on this term, but these boxes are the actual defined color values that are defined by the standards for whatever television system. In this case, this is the digital high definition color system. Different boxes for different systems, by the way. But for now, in HD, these boxes are where the colors are supposed to be, which means these lines have to terminate in the appropriate box. So here's the label. That's blue, that's cyan, that's green, that's yellow, that's red, and that's magenta. Okay. You can see now this shape is a bit more accurate about, because it has to be, we're now measuring the actual product. You can see that red and magenta are closer together than magenta and blue. Right. Again, and that's a perception / technology limitation. Magenta should be mathematically equal parts of both, but because our eyes aren't linear, magenta is actually a bit closer to red than blue. Okay. All right, and I've already said this, so I'm not going to say it again, I don't think. Yeah, what I will say about this is that hue starts at 0. I'm sorry, hue starts at 0. So when we talk about colors, the naming of colors, if you will, we have to pick a reference point, a 0 point. So we pick this 9 o'clock position on the circle as the 0 point, and we just measure it from that. When we talk about colors, and if we're going to use the percentages for colors, which we don't normally much anymore, but if we do use percentages, we start from the 0 point. Saturation 0 point is the center, because it's 0 saturation, and then the measurement from the center to the outside edge is your saturation. And you'll notice that the primary colors are not fully saturated, right? That headroom, that difference between the primary color in the chart and the actual limit is the headroom that we're allowing the system to have to oversaturate if we need to. Because it's recognized that colors aren't always perfect. They're always sometimes a bit high, a bit low. So we allow the color system designed for television has this little extra, what's called headroom between, say, for example, the maximum value of red and the theoretical value of red. Okay. I hope I'm not going too fast. Color spaces. So now we'll talk a bit about that white balance and white point. So color spaces describe both hue and chroma and luma. Right, so the human, we're back to the CIE diagram, by the way. And as you can see here, I have a diagram with the various gamuts and color spaces on it. So for example, the baby blue one in the center is BT 709. BT 709 and REC 709 are essentially the same thing. Why there's a naming difference is that there's different standards organizations in the world. So the International Television Union, ITU, has basically adopted the SEMPTE standard from the United States, and the SEMPTE standard is called REC, recommended .709, and ITU calls it BT .709. I know, right? Welcome to the business. Everybody wants to use a fairly crude analogy, be like a dog, and they all want to pee on the fire hydrant, right? With their own mark on it. It's the same color space anyway. So the baby blue triangle in the center is standard definition and 4K, and then the yellow one, not the farthest yellow one, but the second farthest yellow triangle is the 4K, 8K REC 2020 or BT 2020 color space. You can see there's many more colors, right? So we've talked about that before. Color spaces describe not just what colors, but also their hue, chroma, and luma. Okay. And by changing those three quantities, you move around this diagram. And you move around this diagram in a different way than the vector scope. Okay, they have a relationship, but they're not one-on-one. And this because, and you're wondering why is that? And again, why is there so much green on this CID diagram? Because the human eye is much more sensitive to green than the other two colors. Any diagram of human vision and color sensitivity is always going to have more green than the red and the blue, because that's just the way our eyes are. And that's what this diagram shows, is what our eyes will see. The diagram back here is showing what the equipment sees and what the measurement should be. It's not concerned about sensitivity, it's only concerned about measuring. This is concerned about relating sensitivity as well as measurement. Okay, and why this is because as you add more of the green, things become more noticeable because our eyes are more sensitive to green, right? Okay, where was I? Yeah, so, and of course, just to reinforce the fact that the range of colors that can be represented, and I bolded this, by a particular system is called the gamut. Okay, the color space is the area. The color space is the region of the triangle. The monitor's ability to display that region is its gamut. People will use the two terms interchangeably, and that is incorrect. Gamut is specifically relating to the equipment's ability to, it's like the speed limit. So the speed limit is Rec 709 or BT 709. That's the gamut. That's the limit that the equipment can manage. But the actual shape is the color space, if that makes any sense. Okay. So again, just to quickly compare them, I've isolated the two of them again. So here's Rec 709 again, and Rec 2020. Now, what's interesting about these two, and the reason I like this diagram, is that white is in the same place. Okay, now this isn't always true, but in this case, white is in the same place because it's an equal mixture of the colors. It's the same value, D65, I think is what it says here. Yep, D65 is white. What this means is that you'll notice when the triangles change, in Rec 2020, what's really happening is there's a lot more green, right? There's a little bit more blue and red. The triangle edges move closer to the bottom of the diagram and a little bit closer to the sides. But in Rec 2020, it moves way closer to the top, so it captures way more green. Why is that important? Well, for one big reason in the film business, because green is a key element of green screen. And if you're doing green screen work and you've got more access to green and better green, your green screens will be cleaner, right? Now, a lot of places use blue screens because blue lighting and bounce off blue screens is a more less objectable, but there's still a big place, and as you I'm sure know, there's a big place for green screens still. I say that because about 20 years ago, when blue screening kind of became more of a thing, people started calling the death of green. There'll be no more green. It'll all be blue screen from now on. But as you can see now, with the color space increasing and more access to better greens, you can get a more refined green screen and a much cleaner effect. So there's more colors in Rec 2020. That's the bottom line there. So white point. Remember I said the white point's in the same place, right? And all these triangles, because the CIE diagram is fixed, what humans see as white never changes. The only thing that's changing with these color spaces is how many colors the systems can capture. The humans, the whole shape is human. Everything inside that shape, and everything outside that shape, I'll talk about that in a second, is artificial. It's all equipment-based, technology-based. When I say outside the shape, you'll notice that these S gamuts, these cine gamuts, these top two, S gamut 3, these are DCI, if I'm not mistaken, digital cinema. I forget what the I stands for, but that is the standard for film color systems, which are not the same as video, by the way. Digital cinema and video have different standards. Some of them overlap. The point is, though, that you'll notice there's areas of the triangle outside the CIE diagram. What that means is simply that technology can produce colors we can't see. In this case, ultraviolet. This system can deal with ultraviolet. Okay, your remote control for most devices that is not wireless, any old school remote controls use infrared, so their color space would be outside on this side. Well, we can't see the light, but there it is, right? So what's the point of this? The point of this is that all colors in a color space have a relationship to each other, of course, because it's an RGB system. And by extension, they have a relationship with white, because white is the combination of all three primaries, right? Remembering too that light has color and it changes the rendition. So the light source that is illuminating your work, the light source that I'm in right now, for those of you looking at me in a thumbnail that aren't full screen right now, the light source has a color. That light source colors everything it hits by either adding or subtracting, depending on the color of the light source, the reflected light, the colors in the reflected light, which makes things look different under different light sources, right? And again, you kind of know this, maybe you've learned some of this already with white balance, but this is the key to white balance. The key to white balance is that all light has a specific color in it. So here's an example, and we're going to talk about color temperature right after this, but here's an example of colors of various lights. So here's 4 of them: warm white, soft white, daylight, and crystal white. Now, don't worry about the names too much. There's a couple of names we'll key on. Some of these names are marketing terms. So crystal white glow does not exist in our business. You'll find that at a lighting store because they're trying to make it, they're trying to sell you lights, make it all sexy, all right? But nonetheless, understand these 4 lights have 4 different color temperatures. And again, we'll explain that just a bit later this morning. And those lights will affect the color of the wall. So look at the wall. The light, you can see, if you can kind of tell, looks like one color, but the reflection off the wall is very obviously colored, okay? So by having different colored lights, you have different colors from people. Now, we don't want different colored lights in our business. We don't want the audience to be worried about the color of things changing as an actor or camera moves through the scene. You want it to be consistent. So one of the reasons we worry about a lot of these things is because anytime you break the illusion, anytime you make a mistake and the audience notices it, they stop watching the movie for half a second. Right? So an example of that is someone walks into a room with a gun in their left hand and the camera cuts and now the gun's in their right hand, because when they shot those two shots, they shot them before and after lunch and they forgot what hand the gun had in it. Well, the audience watching the shot notices the gun move and they've stopped watching the movie for a second and go, what happened to the gun? Right? So we want to make sure these things, these inconsistencies, these errors don't occur. So we do what we can to try to keep the illusion going, right? And one of those things we do is change what looks like white. So in the case of these lights, what's happened is that by changing the color of light that reflects on the object, what was white is now a different color. What's called the white point has moved. The white point is this center little dot, which I've actually enhanced from the original diagram. It wasn't on the original, oh, there, it wasn't there originally. I just put it there so you could see it. So the white point has moved on this, in this color space. It has moved because the color of light has changed. It's moved because the equipment, it's not because, so it's not because, how do I explain this carefully? Here's what's weird about this. So we go back here. If you're in a room with these four lights, but let's maybe back it up. If you're in a room with one of these lights and you look at a white wall, it looks white to you. Your brain knows what white is supposed to be, right? So it looks white to you. You don't see these color differences, generally speaking, unless the light is really heavily colored. Like this warm white is actually pretty heavily colored, but this soft white is still not quite white. It's a bit orange compared to this crystal white. But if you had a room with that light on and you looked at a piece of white object, a white piece of paper, it would look white to you. The camera, on the other hand, doesn't have that ability to adapt. The camera only sees what wavelengths are coming off that paper, and they're not white. Your brain, on the other hand, automatically calibrates it. It says that's a white piece of paper, therefore it's white, therefore everything's white, right? So your brain is sort of automatically white balancing for you. And this is, again, one of the traps we get into. People don't see with their eyes on set that the colors look weird. So they don't do a white balance. Looks fine to me. Let's go, shoot. And then you go back into editing, everything's orange. Why is everything orange? Didn't look orange when I was there. No, it won't. Your brain will fix it for you. Your brain can be your worst enemy in our business because it will make corrections for you without your ability to change that. So you have to discipline yourself to remember to white balance when you change light sources, okay? So back to my point, I've moved ahead. So the white point is moved. So what do? I just said that. You do a white balance. You get a menu, something like this, right? And you'll do a white balance on your camera. Now, some of these are shortcuts. Daylight, cloudy, fluorescent. You know, you don't really want to do that necessarily. You don't want to do auto white balance if you can help it. Although, you know, I shouldn't say that. We actually do auto white balance. Never mind. Auto white balance is actually better than picking these pre-selected choices, because these assumptions assume that you know when you pick tungsten or fluorescent as a white balance option. These assumptions assume that you know the color temperature of the light and therefore are picking it correctly. The auto white balance, the camera looks for itself. And it looks for itself, how is that? By pointing it at a piece of object that's white and telling the camera when you hit white balance and it's pointed at a white object, you tell the camera, okay, this is white. So that's what a white balance is. Now, you guys have done white balances. Has Ken explained or anyone explained to you what they are? Yes, no, maybe so. Yes, yes. Okay, good. I just want to make sure I haven't jumped too far ahead of whatever you're at. Hopefully I'm not contradicting anything that Ken has said. It shouldn't be the case. It's all kind of fact. So always best to let the camera choose, but you have to point at a piece of white paper. What you don't need to do with these other choices is do that pointing at a piece of white paper, because you're telling the camera this is that color. right? But automatic white balance, the camera has to look for itself. The danger of this is the piece of paper, the object that you have must be white. So a piece of paper with something on it, with writing, with scribbling, with ink, a piece of paper that's too thin. So you put a piece of paper down on a tabletop and the color of the tabletop comes through the paper, that will alter the white balance. What most professionals have is something solid. They don't use paper. They have a piece of, one of the things I used to tell students is you go to Home Depot and you get a couple of sample chips from the kitchen counter department. And you go in there and say, hey, I'm doing, or my mom's doing, or my friend is doing a kitchen renovation, and they wanted me to get a couple of sample cards of the kitchen countertop. Can I have some white? And get a couple, get a bluish one, get a yellowish one, get like 3 of them, and then take them home. And those become your white cards. And they're free. They're small, to be fair. Doesn't matter how small they are, as long as they're not too far away from your light. But then you get your free little camera color chips you can put in your pocket. You can spend a lot of money and buy the same thing in a 8x8 or 4x4, 4-inch by 4-inch, right? Well, so the difference between the gray card and the white card is you can't, this is the question I just see in the chat, you can't do a white balance with a gray card because there's nothing white to point at. The whole point of a white balance when you have a camera is you have to point at something white, because what the camera is assuming, and I say that because like the camera's got a brain, but what's being assumed is whatever the camera is looking at when you press that button is white. If it's not white, the camera will adjust to it as though it was white, and it could do some radical changes to your picture. So in order to do a white balance, you need a white object, a neutral white. So in this case, if we're looking at 8-bit color, it would be a red 255, green 255, blue 255, right? A gray card is there to help you in color correction later on if you did do a proper, so you do the white balance, you don't have to record that. The gray card, you want to record that because the colorist wants that later. The colorist doesn't want to see your white balance card, right? They want to see the gray card. After you do the white balance, you shoot a camera chart, right? This is the procedure. You do a white balance and you shoot the camera chart. You record that for 20, 30 seconds, and then that's done. And that goes into editing with your color correction person. And then now they can look at that gray and do their reference. So the gray card is really for people after the fact. The white balance is for you right there at the moment. Okay, so that's the key difference. So when you change white, what's happening? What you're doing is you're telling the camera, and we're going to use this cursor a little bit, that this white is now somewhere over here, or it's a bit over here. Well, when you change that, when you move that in the camera, all the colors around it move with it to try to maintain that same relationship. Because remember that in RGB, white is 100% red, green, and blue together. Well, if you do a white balance and that white now moves to be a bit more yellow, because the light is a bit more yellow, the camera will adjust all the primary colors so that no matter where that white is now, 100% yellow or 100% red, 100% green, 100% blue will make white. Your eyes do that for you. Your brain does that for you. The camera needs to be told that. Right? That's the key difference. So the white balance is not just telling the camera what's white, but that's important. But if the camera knows what's white, then it also knows where the other colors are. If the camera doesn't know what white is, it's not quite sure where the other colors fall, and it just records whatever's default programming in the camera, right? Making sense? So this job in the days of film, you didn't do this in film, because the way the film responded to white was fixed, baked into the film. So the only way you could fix this was later on in the processing, when you took the film and then you developed it, and you had to make changes in the developing to move the white to the right spot. And that was called, because it took different amounts of time to get different colors to develop, that was called color timing. And so you may hear people refer to color balancing or color correction today as color timing. And that just refers to the old film practice of putting maybe the red in the chemicals a bit longer, timing it a bit longer to make that white move towards red, right? Because you're changing the balance. Film doesn't need to be white balance because it can't be, but video does. I mean, it doesn't need to be. It'll record without it. Excuse me, I'm gonna pause here for a sec. Sorry about that. Film will record, I mean, video will record without white balancing, but it won't, because in fact, what happens if you don't do a white balance, the camera imposes the default white balance that comes with the sensor or with the processor. Okay, so that's it. Stop record. Oh, where's my cursor gone? There it is. Pause. Stop. I just stop.